2.3, continuity. This is a very important notion, continuity. Right. So let's recall that it wasn't always the case, but for some functions, one can determine the limit of f of x is equal to c just by evaluating at c, right? By evaluating that function at c. Or to say it in a different way, some functions agree with their limits. Right? Some functions have a property that they always that they don't skip, right? That here you're approaching c, and it looks like your value is L, and when you actually get there, the value actually is L, right? So f of c actually turns out to be the limit of the function. Okay. So this sort of behavior warrants a name, continuity. So if the limit of f of x as f equals to c actually is f of c, we say f is continuous at c. And the book describes it as a sort of predictability. You know you're approaching c, and it looks like your function is tending towards some value, and lo and behold, that's the value you get when you get there. There are a couple of other ways of writing this definition. Sometimes you may see it expressed like this: the limit as h approaches 0. Limit as h approaches 0 of f of c plus h is f of c. It's basically the same thing. As h goes to 0, like the c plus h will tend to h. And you get this equals f of c. So that's another way of phrasing continuity. There's another way of phrasing it using the delta epsilons. So it's this: given any epsilon greater than 0, there exists delta greater than 0, such that if, now I'm going to write up something that is not right. Well, no, I just read it. I think that's right. Okay, that's the right thing.
That's the right one, or
This is the right one.
okay.
This is the actual definition of continuity. This is the fancy version of continuity. Yeah, tip it.
What's the thing beside delta?
Yeah.
There exists. There exists. There exists. It's a backwards capital E. Backwards capital E. Just for your amusement, if I make backwards capital E with an exclamation point, it means there exists one. Okay, there exists only one. There exists a unique one. So this is, anyway, I'm just going to, yeah, Rachel.
So why is the greater than 0 thing not used here? Why is it not 0 is less than x minus c?
Okay, yeah. Why don't we say greater than 0? Remember why did we say greater than 0? Why did we say greater than 0 last time? That was in order to
Oh, if x was never actually c.
X was never allowed to be C, right? In this case, you're saying X could be C. X could be C, right? Because you want f of x. Right? You have this value L, and you want to say that at C. Yeah, actually, this is the better. Sorry, let me write it down. Thank you, Rachel. You forced me to make it right. Okay, so look, this would what this says is that you're allowed to take the point at C. You're allowed to take the point at C, and what that would mean is that I don't want to get into this much detail, but what this would force would be that f of C minus L would be less than epsilon for all epsilon. Don't worry too much about it, but this is what would happen. This is what happens. That f of C minus L is going to be smaller than epsilon for all epsilon. And what does that tell you about L? That means that L has to be, if f of C minus L is smaller than epsilon for every epsilon, then L has to be
Equal to FC.
equal f of C. Right? Because remember what we said a couple times. If you have two numbers and the distance between them is smaller than any number, then they must be the same number. So this basically forces L to be f of C. In other words, the limit is f of C. Right? The limit is f of C. But like I said, don't worry too much about this last one. It's just for your, just to plant some seeds in case you go onwards. Okay. So continuity. If you don't want to think about epsilons and deltas, just think the limit is the value of the function of that thing. And then there's a second definition. Let me write it on here. We say f is continuous. Now, very often reading this is just CTS. F is continuous at C. Continuous if f is continuous at every point in its domain. If at every point it has this predictability, then you say it's continuous. It just means it's continuous at every point. Here we talked about continuous at a point. Now we're talking about continuous in general. Okay. So this allows us to rephrase our previous theorems from last class. Okay. So theorem 3 we can write as polynomials are continuous at every point. Right? Or I just say continuous. Polynomials are continuous. Right? Rational functions are continuous at every point in their domain. square root functions are continuous where defined. They're continuous where they're defined. Right, right, if n is even, then we need the point to be positive. Right, we don't, to be non-negative. Right, we don't talk about the square root of negative numbers if we're sticking with the real numbers. In 5, said that sine and cosine are continuous functions. So at the very least, we can rephrase. We can say these things more. This is how we talk. Michelle, do you have a question? Yeah.
At the end of theorem 4, where you
Yes.
say c is greater than 0,
Yeah. So the point. So the limit of f of x is f(x) equal to c is f of c, where the c is some positive.
Okay.
That c refers to the c.
Okay.
Yeah, Emily.
For rational functions, can't that be like a quotient?
Yeah, rational functions. So remember, rational functions are a polynomial over a polynomial.
So is not necessarily continuous enough?
So every point in their domains.
But like for the example that was like 0 over 0, at that point, wouldn't it jump to 1?
Oh, okay. Let me think. But we don't consider that part of the domain, right? Because if it's 0, if it's got a 0 on the bottom, we don't consider it part of the domain.
Even if it doesn't have a value?
Even if the limit exists at that point, we don't consider it.
But wouldn't it have a value there if it's 0 over 0?
So that's the sort of funny thing. If I write x over x, like say I call my function, I have some function r of x is x over x. I know, even though this function tends to the value 1 at x equals 0, one doesn't consider this to have a value at 0.
Really?
Yeah.
But 0 divided by 0 is 1, right?
No, not necessarily.
What
Right,
else could it be?
Yeah, what else could it be? You'll see
Okay.
in this course. Yes, actually, yes. Yeah.
Okay.
Yeah, so it actually depends on how fast things go to 0.
Okay.
So, yeah, you'll see. That's we'll get to. You've probably seen it before. It's called L'Hopital's rule. We'll give the answer to this question. Okay. So, other questions? It's funny that asking other questions makes people be quiet. You think that it would actually make people ask questions. It doesn't. That's sort of the opposite of my intention. Okay. So you can sort of play a game. Not play a game. So suppose you have some function, and the function is x squared minus 6x plus 5 over x minus 5. So this is whenever x is not equal to 5, and it's 4 if x equals 5. And I'd like to know, is f continuous? Or where is f? Where is f continuous? Where is this function continuous? Okay. And you can basically answer it using this stuff and the stuff that you did from last class. So take a minute and see if you can give me an answer. Where is f continuous? Is it continuous everywhere? Is it continuous at what points? Okay, what's the answer? You can give me an answer. Who would like to make a guess? Can anyone tell me one point where this thing is continuous? 5? Okay, so x equals 5. Why? Why? Well, you want the limit of the function as x approaches 5 to be the value of the function at 5. Right? Is that true? Is the limit equal to 4? Yeah, it is. Right? You work it out, right? It turns out that you can do some cancellation. So you get x minus 5, x minus 1 over x minus 5. Right? Your function, right? As you tend towards 5, you can cancel these things. These things are not 0. You can cancel them out, right? And you get 4. And of course, the value of the function at 5 is defined to be 4. Right? And so the limit and the function agree there. Okay? So at 5, it's continuous. And what about any other point? All points, right? All points, exactly. Right? And at all points. Because at all other points, it's a rational function, right? And we said that rational functions are continuous wherever they're defined, right? Yeah.
Even if you didn't say like x doesn't equal 5 there, and then it's 4 when x does equal 5, would it still be continuous because it's not in the
So, right, are you saying if we erase this part here?
yeah, and the x doesn't equal 5.
Okay, so yeah, in that case, you have a function which at 5 approaches 4,
Yeah.
but then there's no value there, right? And so we say it's not. We wouldn't say it's continuous because you want the limit of the function to equal the value there, but there's no value there.
Okay.
So we say no. We say no. It's not continuous. It has a hole in it.
Okay.
Yeah.
Is that a rational function?
This is a rational function.
So then, is 5 in the domain?
It's 5 in the domain. So this function is continuous outside of 5.
Oh, okay. Sorry, I was
Yeah,
thinking.
5's not in the domain.
Okay, okay.
Yeah, 5's not. Okay. So yeah, actually, this brings up another term. This is what's called a. This is a function. If you're looking at this function, then this is a function that has what's called a continuous extension. In other words, it has a hole that you can fill in and make it continuous. Okay. So there's this term. It's sort of a strange thing for the authors to include, but they include this term, continuous extension. Basically, all it means is that function has a hole. Which, if filled in, makes it continuous. Filled in properly, say. Which can be filled in such a way as to make it continuous. Right. So this is a function that actually has it. If we look at this function, right, it has this hole there, but you can fill it in and make it continuous. So it has a continuous extension. So you could have something like this, right? this function would not have a continuous extension, because no matter how you fill it in, it's still not continuous. So no continuous extension. Let me give you another. Okay, so let me go on and on. Another sort of important topic: continuity and arithmetic. So just this that. If you have two functions, if f and g are continuous at some point c, then their sum is continuous there. So if you have functions that are continuous at a point, then their sum is continuous. And if you understand the definition, then you should sort of be saying, well, of course, right? Because let's think of what this means. What do you need for this thing to be continuous? Just as a practice of, do we understand the definition? What do you need for this to be continuous? What do you need for the limit? What do you need? What would have to happen?
Limit as x goes to c.
Don't put it up.
Oh, sorry.
But go ahead.
The limit as x goes to c would be g at c,
So
or
the
f
limit.
at c plus g at c.
So you need the limit of the values in the function to be the f of c plus g of c. Right? You need this to be equal to the function evaluated at that point. Right? Now, does that happen? Does that happen? Well, let's think. Right? Is that true? Right. The limit of f plus g. We know something about this, right? The limit of f plus g is equal to what? Somebody said it? Say it again? Yeah, so this is equal to f of x plus g. F of x plus g of x, right? And then when you take the limit, you're going to get the...
The limit of x versus c of f of x plus the limit of x versus c.
Right. We have this rule about the limits, right? The limit of the sum is going to be the sum of the limits, right? So you get the sum of the limits. Right? And then why is this f of c? Is this f of c? Sure, because
There's a theorem that says that you put in z. I don't remember.
it's not a theorem, but rather does somebody joke?
It's continuous.
Yeah, because it's continuous, right? Because we said f and g are continuous. Right? F is continuous, so this is f of c. G is continuous, so this is g of c. Right? And because those guys are continuous there, the sum turns out to be continuous. So anyway, this is how this sort of thing. This is how this thing works. It's kind of dull. It's not exciting. It's not exciting. That's why I try to balance things out and throw in strange things to keep you at least somewhat interested. Yeah. But this is definitely not exciting. but this is how so it goes. Yeah, I should say that, you know, a lot of math is not exciting, or some math is not exciting, and some math is more exciting. I'm not gonna pretend that this is great. But this is how the argument goes. It's simple. Okay. So that's just explaining. So one, the sum is continuous. Other things that happen, the product is continuous by basically the same sort of argument. Third, any constant, right? So remember alpha we're going to use to denote some constant. Any constant times the function is continuous. And then four, any quotient is continuous wherever g of c is non-zero. Okay, so let me ask you a question. If I make a function that's sine x over x, is this continuous? Or rather, I should again ask, where is it continuous? Where is this thing continuous? And now, just take a few seconds and answer it. Where is it continuous? Joey, you're banned from speaking. Okay, you should be proud. I should explain that if I ban somebody from speaking, they should be like banned from speaking. You should keep count, like how many times. Hey, Ellen.
Is it continuous within its domain?
Within its domain, yeah, right? Because we said that any quotient of continuous functions can be continuous wherever the bottom guy is non-zero. So at least we know that the top is continuous, the bottom is continuous. So this is continuous on all of R, excluding the origin. Okay. On all of R, excluding the origin. Excluding 0. And we saw last time that that this thing has a limit as x tends to 0. Do you remember? As x tends to 0, this thing tends to 1. Right? So in fact, we could fill this in. This thing actually has a continuous extension, right? So in fact, it has a continuous extension. Right? You just fill in, you just create the new guy. Right? You create this new guy, which takes the value, the proper value, takes the proper value at the right place. This thing had a hole at 0, but it had a limit. It tended to a limit at that place, and so we can fill it in and make a continuous extension for it. Question? Yes.
Sorry, this is a question I had before
Yeah.
about like filling in the hole.
Yeah.
Like how would you fill in the hole? Because
Here we've done it.
with ones,
Yeah.
or like 4, okay.
Yeah. So our previous function had a hole in the function, right? I don't know whether it's some function, right? It had some hole in it, but it actually tended towards a limit there, and so if we give it the value 1 there, then it becomes continuous. Okay. The last important theorem about continuity, well, that's not true. Another important theorem about continuity is about continuity and composition. Continuity and composition. So actually, let me write this in here. Sorry. Continuity and composition. So you have one function that's continuous at some point, and you have some other function which is continuous at f of c. So you have one function function that's continuous at c, you have another function that's continuous at f of c, then what am I going to say? What's going to be the punchline? Taylor?
F of g of x is continuous.
Let's see, f of g is continuous. Let's see.
Yes.
Almost. Yeah, you basically got it, but in the so like you've got one function here, c, f takes c to f of c, right? You have another function, g, which takes f of c to g of f of c, right? This guy is continuous here, this guy is continuous here, and then their composition will be continuous at this thing here. Okay, so the composition, which will be actually g of f, but yeah, the composition in the right order will be continuous. So g equals f is continuous at c. So for example, if you have two functions that are continuous everywhere, then their composition will be continuous everywhere. And this is actually really powerful. So for example, to show you how powerful it is, if I say, what's the limit as x approaches pi and 2 of root sine x plus say sine cube x plus 2. Now let's just say root sine x. No need to go crazy. Okay. What's the limit of root sine x as x approaches pi over 2? It'll be 1, right? And why?
And then
Right. Right. But you have to realize what you're using. What you're using is that the square root function is continuous, right? And the sine function is continuous, right? Right. The sine function takes this thing in. It's a continuous function. The square root function is continuous at 1, and so you can just evaluate, right? So this is going to be the square root of 1. Okay, so be aware, we're using the previous example. Yeah, Alfred.
So they said something like, if they asked for an x value that was actually negative for the sine value, then what would happen?
Then it wouldn't make sense, right? Because your function is not.
So that would have been no limit?
That's right. Yeah, it wouldn't make any sense. Like, there's no value there.
Okay.
Let me make one comment about continuity that I should have made before. Right, when we say like the limit of f of x as x equals to c is f of c, so this is actually a pretty important remark about continuity. Another way of writing this is like this. The limit of f of x as x equals to c is f of the limit of x as x equals to c. Right? Because the limit of x as x approaches c is just c. Right? So you might say, why did I expand this c into something seemingly so complicated? But this actually illustrates the important idea about limits, about continuity. What continuity means is that you can slide the limit past it. You can slide the limit past it, right? That is, I can take the limit of the function, or I take the function of the limit, right? I can take the function first and then the limit, or the limit first and then the function. Okay, so that is, continuity means that you can switch the order of function and limit. Okay. Continuity means one can commute limit and function. That it's commutative. You can change the order, it doesn't matter. Right? And so what we're doing here is we're sliding the limit through the square root sign, and then we're sliding it past the sine function, and this is really the square root of the sine of the limit as x goes to -2 of x. Right? So you can slide the limit past these guys, and you end up with the square root of sine of 2 nearly 1. So that's actually another really useful way of thinking about continuity. It allows you to interchange limit and function. Okay. So let me see if I can finish up what I want to say here. There are a couple of things in this chapter that I would call sort of deep properties of continuous functions. Deep properties of continuous functions. And the first is something called the intermediate value theorem. So you have some function